Okay, I'm back. I think I'm back. I'm back on Twitch. All right, let me get Discord up and running. All right, I am I should be up on Twitch and up on Discord at the moment. All right, let's see. This is slightly tricky. Let's see. All right. Getting things kicked off here. I want to get ready. The way the lectures have been going so far, it's been about what we've been doing this for a couple weeks now. I mean, it feels like a couple weeks now, but it's been literally one day. Hello, somebody's joined. Kathy, could you mute your microphone unless you have a question? So we'll we'll do it that. We'll deal it that way. So yeah, a little bit of the background for those who haven't watched yesterday's stream yet. We are up on Twitch. So if you want to go to www.twitch.tv/erasermice, you can watch it on Twitch. I think that gives you probably the best quality, but there might be a little bit more lag, and we can't do the real-time voice chat on Twitch, obviously. So first things first, give me a thumbs up. If you're watching this so far, what, four of you, go ahead and give me a thumbs up on Discord so I can know you're reading. I see a couple of people joining the chat room on Twitch as well. That's good. All right. So the challenge is, of course, yesterday I did a lecture from 12 to 2 for about an hour and 40 minutes or so, and that covered. It's basically the same material that we're going to cover today. So what may very well sort of happen today is it'd be the same thing. So I have a feeling today might go a little bit quicker, and ideally what I would love to have happen is that the Monday and Thursday classes would sort of be dress rehearsal for the Tuesday and Friday classes, which is normally what happens anyway. So if the Tuesday, it's almost preferable if you miss one of the lectures, watch the second one, because chances are that will be the more concise one. So if the Monday one is really good, though, then you can just watch the Monday one, and we don't have to stream everything all over again on Tuesday. So they're always available. Twitch has them recorded. Discord doesn't have them recorded. So if you do want to watch them after the fact or off hours, you have to go over to Twitch to see them. Okay. I'm not going to get into Google Hangouts or WebEx or any of that stuff right now because this seems to be working really well and reaching the most people. I will say, let's see, it's 10:03. Attendance isn't quite what it was today as it is yesterday, or quite today as it was yet, or something. Anyway, I'm trying to be funny, I guess. Okay, so the topic, I guess I should do some summary. So you've all heard in terms of the way that grading is going to be going with regards to RPI as a whole, that you can declare any of your courses up until May 15th to be pass no credit. What that means is basically if you need to pass a course in order to fulfill a graduation requirement, whether it be a comm intensive course or a data intensive course or a major specific course, anything like that, you can still designate it a pass no credit. So you'll just get a pass on your resume, your transcript, and so on. So you have that. You can decide that right up until May 15th. So if you're not doing, if you don't want your grade to show up on your transcript, you can do that. So I can't imagine most people in this class fall into that category, but if you do, that's totally fine, and you have lots of time to decide. One of the main things, of course, I want to do is keep people engaged. You should all be still coming around. You want to, certainly you're going to want to get the projects done. You can't just check out and expect everything is going to be completely, okie dokie. So we want to see you continue. In order to do that, I also want you to be very much proactive. I'm going to start downloading the projects earlier rather than waiting till after they're due, so that I can kind of see how people are moving along, the number of people who have actually done things. I can see your updates and all that kind of stuff. And if I need to talk to you earlier on, or if you have a question, I can then just go right to your code and we can have a discussion on Discord about specific things. So it's going to be really, really, really important for everybody to get their stuff up and running inside of the Unity team server. So that kind of stuff. So Unity team server. Oh, due dates, they're in flux at this point. Hopefully I didn't want to change them too much because we do want to have 2 projects this semester still. So we'll see what exactly that means. I expect to have some announcements later in the week with regards to all my classes in terms of my expectations for the due dates. It definitely, now things are going to be a little bit more self-paced because you are going to be potentially watching some of these lectures at your own pace and so on. But as far as real time goes, as far as making sure you get a hold of me, seeing issues and all that kind of stuff, you can always email me. But actually, Discord is going to probably be the most immediate kind of thing, because even if I'm streaming, I'm going to be live on Discord while I'm doing it. I'm always going to be checking Discord as much as I can. So hopefully that's going to be the most immediate way to get a hold of me with regards to anything. So other things, as some of you may have noticed, I started posting sort of the extra Twitch sessions. I posted one last night about mouse aiming. So I'm going to just continually, kind of when I have time, post things like that. I'm going to try to record them, eventually post them somewhere else, but you can count on them at least being around for 2 weeks. So keep up to date on them. If you haven't subscribed to me on Twitch, go ahead and do that, just so you'll know when I post things. I'll try to simultaneously announce that I posted them on Discord as well, so you'll receive notifications. At the beginning of, or let's see, in the Discord general, I made mention of having some interesting announcements at the top of the stream, so I might as well get to that, and it's open to everybody. So the idea that I've had, and I posted this as a trial sort of to some friends on Facebook and whatnot, is if you're familiar at all, and I'll show you this game that we had as demonstration. You're all pretty familiar with it by now. Our little our hero in the RPG here, and the idea similar. You see I zoomed out a little bit, and let's see, he's glowing here. I'll talk about that a little bit. But the idea was simple, that I've added the mouse aim, so don't worry about that. The idea was simple. Our little hero shoots bullets and they hit things. And one of the demonstrations I had in the Tuesday-Friday class, which this is, was this idea that you could have this exploder. And the idea was that if a bullet hits something, it then explodes and goes off and then basically can hit other things. And then there's also this notion of, well, what happens, we had this in class, what happens if I override that explosion behavior that it can only ricochet once? And instead now, it can ricochet every time it hits something. Kind of mayhem. Let's see how long this lasts here. Let's see. Yeah, it's going to destroy these buildings. Congratulations. It did it. So the interesting thing about that is it actually is a pretty good demonstration of kind of going viral or exponential growth, which isn't exactly what happens in the real world when you have a virus out there. You have some sort of infectious disease. There are, one of my friends pointed out, yes, they don't grow necessarily purely exponentially. They're more logistic functions in that, based on resources dying out and all that. Well, we won't get into epidemiology much, but anyway, using simple concepts like this, like when the game ricochets and infects something else or bounces off something else and can damage something else, we can model these kind of real world things. So the challenge to everybody, I'm challenging myself with this. I'm going to kind of hopefully chart the development within my Twitch stream as part of continuing the work in the class and demonstrating the concepts that we're doing in class. And this is not a substitute for, by any means. We're going to continue. The curriculum is going to remain the same. We're going to keep going through. You don't have to change your gears. No flex necessary here. But if you are so inclined, or potentially want to work directly, I can't open up to everybody because even the Unity team stuff only allows me a certain number of seats and whatever. But there's the possibility of some kind of deeper levels of collaboration if we want to really try to do something that it can be. It's not going to necessarily be a predictive model of what we're not going to try to. You're certainly not going to set out to cure this pandemic using a Unity 2D shoot 'em up game, but we can use it to illustrate certain things in the process. So if you want to take it up as part of your project, or if you want to, if you have the bandwidth and want to potentially do some collaboration on it, that's cool. I'll reach out to some of you based on some of the work you've been doing, and even the other class and so on, and the other classes that I teach and some of the other faculty, to see maybe we can do something, and that helps just sort of educate people on the way these things behave. Obviously, the type of data objects and scripts and so on that we're going to need potentially could grow to be a lot more sophisticated than what's really required for this class. If we get into things where we're saying, oh, okay, there's, instead of enemies and friends, we get into things where there are, just people in the real world, and they're going to, cough and spread virus and whatever, and they may be inclined to wear masks, or maybe they don't, or maybe they decide to walk around, or maybe they don't. Maybe they're of a certain age, and we can really kind of start building in kind of AI elements and behavioral elements into these things that, again, could be educational, could be interesting. So why not? Why not? If we can educate some people, as I said to somebody, if I can convince somebody not to, accidentally infect their grandmother in Tallahassee, so be it. This is not about alarming people. This is really just sort of about educating people who might not, might not get the message otherwise. So that's one opportunity. I'm going to continue to develop that in my Twitch stream, and as part of the stuff I'm going to demonstrate, work it in as best I can. So that's the scoop on there. So okay, that's that. If you're just tuned in for that announcement and you're from the other class, something like that, I think that's about it. So we'll move on from there. Whoops, somebody just joined and their mic is on. If you could turn your mic off, that'd be great. So let's see. Any questions? Go ahead, shout out on either Kathy. I think Kathy, it's your mic that's still on. It's kind of coming in real loud every so often. All right. I've discovered I can force mute people. I don't know if I should do that. We'll see, hopefully. You got it. Okay, great. So, any questions? Oh, I'm still, I'm not normal. I'm not normal. I'm not a regular at streaming on Twitch, so I'm getting to know that, getting used to that a little bit. So, if there are no questions, whatever, what I want to do in class, a lot of the time, I'm going to be asking you to react to my statements. So, like, when I said give me a thumbs up, telling me that, just so you're paying attention, or there's any questions or something like that, try to use your reacts to basically let me know what's going on. So I need feedback, but I don't want to just have mayhem of 50 people all trying to talk at once. So a little bit of a challenge, but we can get to it. Okay, if you do, the normal, normal kind of things, we talk about, how's everybody doing? If you have any issues, if you've seen, other classes that are having problems, need some help in terms of some guidance on using social media and streaming and whatnot to get things up and running, let me know. This is all part of the public service announcement in general. All right. So if I forgot anything, if you do want to go back to the other stream and watch that as well, from here on, I'm going to sort of cover the same material of the last stream. So, all right, where are we? So I thought I had, let's see, code, physics, and so on. let's see, present. Now, another thing, obviously you can watch the stream here, and it is easy enough to read it, hopefully. But if you do want to go to LMS, the notes will be available. There's actually a lot of extra stuff on LMS available now. I've included 2 lectures that we created. We kind of jointly created these a couple of semesters ago when someone else and I were teaching the class. I wrote the original Asteroids shoot 'em up game, and then he did some lectures and stuff based on that and kind of changed and tweaked a little bit. So I kind of liked his lecture notes, and I like seeing it from a different perspective, the same development as well. So that's up there for you, but don't necessarily, none of this is gospel. Your games can be considerably different. Like if you look at the RPG that we're working on so far, it's obviously quite different from the Asteroids shoot 'em up kind of game. So hopefully it's a matter of you guys kind of taking the concepts and running with them. So that's up there. I've posted lecture notes, a few lectures in advance, based on, hopefully, we'll see where we go, see how much time is taken and whatnot. So there's going to be lots of information there, but always just double check, reach out to me on Discord about where we're at. If you want to get ahead, by all means do that. If you want to, look at other stuff, if you find other really, really good resources, there's obviously lots and lots of really great Unity resources out there. And there's, I have older videos and so on. Certainly, call me out on my changes. I've made changes to my approaches on things. So if you watch an older video of mine and I'm doing something a different way, and you want to ask why I changed my thoughts on it, you certainly can do that. Last but not least, before I get into things, since everything's in flux, and if you do want to pitch your project being considerably different than the typical shoot 'em up and then the typical platformer, if you want to somehow combine the two or do something a little bit more without getting too far afield, because obviously I still do have, there's lots of you out there, so I can't completely run off the rails, but I'm up for, pushing the envelope, we'll just say, stretching what we're capable of doing. Okay. So let's talk about running code on time and what that means. So we're going to look a little bit more, we're going to review a little bit of physics, and we're also going to take a close look at execution, about when code runs, the type of code that you're writing in your scripts, in your monobehaviors, when it's actually being run, and what the implications are, especially with regards to physics. We're talking about simulations here, and so obviously accuracy, smoothness, and all that sort of thing matter a lot. And we'll dive right in, shall we? Okay, so first, there's a couple of slides of review here. I'm going to go through kind of quick at this point. So the current scene is a collection of objects displayed in a hierarchy. Game objects start off just being a name, a tag that are on a certain layer, and they have a transform. Okay, so you're kind of used to that. Hierarchy has a parenting structure, so you can have game objects that are children of other game objects, for example. That hierarchy does imply a certain amount of structure, like parents might have things happen before children do, or the order that they appear as children within a structure that may have an impact on the order that their code gets executed, like their start functions. It's not running every start function simultaneously. It's going to ultimately, Unity's running one right after the other. The order of things in that hierarchy are going to have an impact on that. Normally, each game object contains at least one, but possibly many components, and these are usually, you've seen them in your own code. Those components are based on monobehaviors and have certain built-in things, right? Many of the components are provided to you. You've seen transforms, renderers, cameras, and so on. So we write components ourselves. They are new C# classes that do inherit, and we're going to come back to inheritance more and more. They inherit from monobehaviors. So they, by default, they're going to do a whole bunch of things that monobehaviors have just kind of built in for them. So for example, when you click the play button, then Unity automatically iterates over all of those game objects in the hierarchy. It runs through one thing, then the next, then the next, then the next, everything in the scene. It iterates over every component. So it goes through every collider, every script, everything, and it's basically a big nested for loop, right? For every object in the scene, do this. Call their start function, call their so on and so on, right? It invokes first, it runs, it executes that start function for that component if it has one. Okay, right? We've seen the start function. And then after that, on every frame, Unity then iterates over every game object, checking to see if that component has an update. If it does, it runs that, right, in a loop. So we have this basically, it's kind of a while loop overall. So the higher side, the higher level, higher part of the hierarchy is just this while loop that says, while the play button is pressed, run through this loop. And then it's going to sit there. Hopefully I'm not making too many squeaking noises by, sorry. Run through this while loop, and then inside the while loop there's for loops, so there's kind of nested loops with regards to the actual Unity engine. Okay. Now, one thing we haven't, maybe we've sort of touched on a little bit, is this notion of the awake function. Now, the awake function we haven't seen too much. It's very, very similar to the start function. It actually happens before the start function. So every MonoBehaviour, everything that inherits from MonoBehaviour, excuse me, potentially has an awake function. That function is called before the start function. Well, why? In some cases, you want to set useful information that all other things can use in their start function, right? So if you really want to set some sort of global variable that everybody can refer to in their start function, you want to do that in the awake function. Now, you can't necessarily say whose awake function happens first, and you can't say whose start function happens first. That's why you have this concrete difference between an awake function, an awake event, and the start function, the start event. Okay, so this way you can count on this happening before that, right? Again, it's a little trickier, so everything that start functions might depend on should happen inside of awake. Things that awake depend on, well, you're going to have to be careful there. So that's a trickier one, but hopefully I haven't seen too many instances where people had to worry about that. An interesting thing about the awake function is that that function will run even if the component is disabled. So if you disable a component but it's still part of your object, it will still run. You have to actually deactivate the entire game object, not just disable it, in order to prevent that from running. Okay, there's a difference between deactivating something and disabling something. The idea is that something might be enabled later. So we have the on enabled, on disabled. That can happen at any point during the game. And if it happens, then its start function is going to get called after that, and so on and so on. So we have to make sure still that the awake function for each of those components, each of those scripts actually got called, which is why awake happens no matter what. Okay. So we have the awake function, the alternative to, that's the one that happens before start. We also have this event, this function called the late update function that each of your components can also have, part of your MonoBehaviour. And it's similar to the idea of awake and start, but except late update happens after update. So it is another update function. It runs in the main loop where update lives, but it happens after all of the update functions have run in this frame. So if you need to do something kind of globally, or that depends on the behaviors of all the other of all the other objects that are being updated, you use late update for that. Right? It runs after the updates for the whole frame, and after all animations have also been computed. So anything that is being updated as part of an animation is also happening right before late update. This is useful when you want to have something that happens in the same frame, but guarantee that it happens after that, right? The order of all the things that are in here, whether they're late update or update, normally that order is arbitrary. So you have to be careful. That's why we have these two, just like the reason we have awake and start. So this is sort of what it looks like. This is the idea. You have awake that you can count on happening before start, and then after start happens, you have updates. So you can count on that happening at least once per frame before late update happens, and then they go in a loop. So functionally, once you're inside of a loop, it's kind of like, well, which happened first, who knows? But you do. The important part is that you know that everything that has an update function, those happen as a group, and then everything that has a late update function, those happen as a group. Okay. So even though we have, I'll use my mouse here, there's this loop here. This is the while portion. What's really happening is you have also a for loop sort of happening in here. right? For every object that has an update function, this happens. And then for every object that has, excuse me, every component that has a late update function, they all get called, right? So there's this grouping that goes on, and that's the important thing, right? So these are MonoBehaviour functions, right? We have start, we have update. Now we also have, like for example, we had on mouse down, our input functions that you can have events based on certain things happening, like when the mouse is clicked while hovering over the object that you're currently on, you get an on mouse down. So you don't have to necessarily just look for a mouse click. You can actually get a mouse event just like a collision event. Okay, so the mouse down is sort of a special version of a collider, but it's just on mouse down that will say, did the user click while hovering over this object, as long as the object had a collider 2D, because it still has to figure out, okay, what does it mean to really click on that object? But that's a different type of event that you can see. Now we also have our on collision enter 2D, we get our collision from, and then we also have like our on trigger 2D and so on and so on. So we have those other kinds of functions. Now, where do they happen? Where do they get called in all of this? Well, we're going to complexify. We're going to create a little bit more complexity to our loops here. So before update and late update, we have, for example, the on mouse functions. So this would be on mouse down or on mouse. You know, there's a whole class of these. So they will happen as a group. Then update will happen as a group. Then late update will happen as a group. Okay. So these classes of, or these categories of events, they will get run as a group. Now, later on, we're going to talk about creating our own events, and it's important to understand this right now, that this sort of groupings do occur, that according to the certain types of events, they will get executed as a group. Right. So we've seen all that happen. Now we know that there's also physics. I didn't say in here, well, where did my on collision happen? Where are those at? Well, they're different. The physics step is calculated in its own loop, right? There's a different loop, another while loop, basically, that gets executed simultaneously, sort of simultaneously, with the main update loop. Okay, so you might ask, well, why is that? Why can't we just run everything in our normal main update loop? Well, it's about speed. It's ultimately, it's sort of about speed. It's sort of about simulation. It's sort of about a lot of different things. So we're going to revisit physics now. So this is why physics has its own thing. And this gets, we'll try to go through kind of on the quick side. We've talked in class a couple of times about why we like to use physics for the simulations, because it's going to work like the real world. The interaction between objects is going to be better. The way the player moves around in the world is going to be more interesting, more rich, more robust, and so on, as opposed to really calculating all the nitty-gritty of positions around. We're going to leave that part up of translating objects around. We're going to leave that to the Unity engine, but we're going to rely on physics. Now, as part of that process, things are not really, the computers aren't analog. Computers are digital. Computers are discrete. We calculate things based on certain steps. We calculate things at certain times, right? We don't just say, oh, okay, I want to figure out from point A to point B. I always have to say, well, where am I in the time? How far should I move during that time step since the last time I was called? That sort of thing. Okay. So speed, for example, right? Speed is distance over time, right? We have miles per hour. That's what gives us our speed. We understand speed that way. How much distance changes, the position changes in a given amount of time, is speed, right? You move a certain distance, how much that changes over time. And typically, though, we talk about speed as an immediate, having an immediate sense, right? We're currently traveling at 65 miles per hour. That's our velocity at this moment. It doesn't tell us how far we've traveled unless you say, how many hours have you traveled, right? Just saying I'm driving at 100 miles an hour doesn't mean I've driven 100 miles. It's quite different. So distance is actually the accumulation of speed over time. It's kind of scary. I'll warn you, something's about to jump at us here. This notion of accumulating things over time. Distance is the accumulation of speed over time. So what we're doing is we're taking the sum of speed values over some, at some increment, some incremental value. We scale it by the time slice, the amount of time that happened. Remember, time dot get time, or time delta time, right? So we know exactly how much to move during that period of time if we're actually calculating it, as opposed to physics, right? So if we sum up all those, it will add up. That sum adds up to the total change in distance. So, at the end of 50 updates, we've moved a certain amount of time, a certain amount of distance on the screen. Right? So let's introduce physics a little bit. Right? Force equals mass times acceleration. Now, acceleration is an expression, has to do with, we are accelerating something. In our case, we are accelerating motion, right? So ultimately, the velocity is changing according to acceleration. Okay, there's the hint there. It's sort of doing that. So, pardon this. I always run through this and then I forget. I need to update this slide. At some point, I scaled it and it went into left field. Sorry about that. So what is acceleration? What is velocity? Let's express it in terms of some math. Don't worry, there's not going to be a math test. So, but just hopefully none of this should be too shocking. Hopefully you've had a little bit of calculus by now. Maybe some, I don't know if some differential equations or not. Or anyway, as long as you had a little bit of physics and a little bit of math, we'll leave the actual calculations to the future. Is that okay with everybody? Give me a thumbs up. Okay, but we have these two things. Velocity is the change of position over a certain amount of time. dx represents that change of position. We're talking about strictly in one-dimensional right now, just for so we have, this is going to be, we're talking about speed, velocity, acceleration, all that kind of stuff, one dimension at a time. We can kind of separate that out for ourselves here. So v equals dx over dt, right? Some small portion of time, some small distance, right? The change of distance over the change of time. So 0.5 seconds, we went, this is how far we can go in 0.5 seconds. This is how far we can go. How many miles per hour? Look, miles are at the top, hours are at the bottom, right? That's the amount of time we've passed, potentially. Now, over here, acceleration, right? Here's where the acceleration gets interesting. Acceleration is the change in velocity over time, right? So velocity is happening miles per hour, and then how quickly we change that velocity, that's our acceleration. That's how far. We don't usually think about that, right? That's our accelerometer, our gas pedal, right? How hard you stomp on the gas pedal, how much you're changing the gas pedal, that's changing your acceleration. So, whoops, let's go forward. Now there's something else. Well, we can think of this. Look at it. We can call that out. We can say, okay, well, acceleration, if we try to express that directly in terms of dx and dt, or our distance and our time, we could see it as actually the second order, right? We are saying the change in the change of x and the change in the change of time, or over this smaller increment of time, right? So these two are related. We can actually express them in terms of one another. And lo and behold, oh my gosh, we have some integrals. This is one of those weird times where you say to yourself, okay, when am I ever going to use calculus? And this turns out to be one of them. But you don't have to worry about it too much, right? So what's happening is that we can figure out the distance by accumulating all those little slices, right? Those little slices of velocity over the course of time, those little changes, our new velocity can be expressed as those changes in acceleration over the course of time. And then we can say, okay, at any moment, any new moment, after any amount of time has passed, we can say, okay, the velocity last time around is changed by the amount of acceleration that we have expressed, right? So velocity, a new velocity, is acceleration times time plus the initial velocity. All right. So here we are. We can say, okay, our new x position, as we're moving, is the accumulation of, according to the velocity, and the change in the velocity according to that acceleration. So that's how we actually get these physics functions here. Now, the good news is, if you are using the physics engine, this is all going to happen for you. So we don't have to worry about it. But we do want to be careful about how we interact with what's going on in the physics engine in order to get the smoothest results. Okay. In the ideal world, we have this linear change. We have, the analog world. If we can be really good about pressing the accelerator, or we stomp on it, and then just the reaction time of the motor in our car is going to give us some type of increase in velocity, some type of acceleration. And in the ideal world, these things are linear, right? And x, now we have a velocity, we have a time. X is that accumulation over that. So as we set the limit of, kind of making that time slice smaller and smaller, we're subject to those limits. That's the problem, right? So in the computer, we have to deal with these discrete time steps, right? So we have potentially some unit of time, some granularity that we have to deal with, right? So every frame, ideally, every frame would be the same. Every one of these little steps that we're using for our integration are the same. And ultimately, if we have a reasonable version, well, actually, let's see here. If this is the accumulation under that curve, and this is the accumulation under that curve, they're quite different. There are gaps under one compared to the other, right? Someone pointed out in class that, well, the performance on their machine, their computer, seemed to be kind of different than my machine. Why is that? Why, if we're just adding forces, we're doing the same thing, the code is exactly the same, or so it seems, but yet the response of my character versus your character seems different. Why is that? Well, if you're using update to update your physics engine, to update your physics parameters, specifically like adding a new force or modifying the velocity, you're subject to the error that potentially creeps in between here, right? The smaller the increment, the more precisely it's going to fit that curve, right? So little bits of error in there. If you have very small slices, the bits of error are going to be very small. If you have larger slices, the bits of error are going to be quicker, or going to be larger. And eventually things will kind of catch up, but in the case if you're trying to simulate an acceleration or velocity, they're not going to work exactly the same. They're going to be sort of responding differently in this case, right? So that's fine in the ideal case, even, or maybe you can worry about that, or maybe you can kind of predict that, imagine in the ideal case. But now in the real world, or even in our real simulations, as the player's moving around, typically they don't just accelerate, constantly and make things nice and easy for you. They move up, they speed up, slow down, and so on. They act like this curve, for example. And now we can see if we're taking a time slice at a particular time and we're trying to integrate over that, suddenly we're getting errors in all sorts of different directions. Sometimes we're overshooting, sometimes we're undershooting. So things are starting to happen according to that. And that's going to be compounded by something really interesting. So this error, let's look at our error and see how potentially that error accumulates. So imagine we have a car that starts at rest. So our car is stopped, but it's going to accelerate at a rate of 10 meters per second squared, right? So the question is, where will that car be after 10 seconds? Now the analytical approach, of course, you've got physics and you want to, pull out your calculator and just work this out. Half of acceleration times time squared plus the velocity, initial velocity times time. Okay, that's going to get us there. That's going to give us a nice number. We're going to say, okay, after 10 seconds, x is going to be 500. Piece of cake, right? Everybody got that? Give me a thumbs up. All right, no thumbs up necessary. But now, computers, we have to be numerical. We have to be digital. We have to be discrete. So we can't just say, at the end of 10 seconds, where do we want to be? We have to say, at the end of 0.1 second, where do I want to be? At the end of 0.5 seconds, where do I want to be? Those tiny little increments, because you want to move objects on the screen at some smooth rate, right? You want to update things every frame, potentially, or hopefully every frame. So we can't just say at the end of 10 seconds. That would be really kind of morbidly slow animation. So we have to do things like say, okay, we start off at t, time is 0, position is 0, velocity is 0. And then at some interval, we're going to calculate the new values. So at time 1, we come along, we say, okay, we haven't been able to move yet because at time 0, we had 0 velocity. We haven't accelerated yet. We can only accelerate over the course of a certain amount of time. So at time 1, velocity is going to hit 10 finally, and we're going to actually be able to calculate some change in position, but we didn't do that yet. So next time around, at least, we can say, all right, now time is 2, velocity is 20, so position now is 10. We've moved, right? We can start to move, and so on, and so on, and so on. So you see, eventually, our velocity is speeding up, and we get to the end. We finally get to a velocity of 100 at the end of 10 seconds. But at each step in calculating according to our initial velocity, the problem is that we have this error that accumulated, right? We could never instantaneously, we could only discretely change our position. We can only discretely change our velocity. So that's potentially where error comes from. And there's always going to be some kind of error. It's not going to be the perfect world. We're always simulating. All right. So here we are back to our fancy function. And hopefully we are able to slice things up at that nice interval. But the reality of that is it really looks something more like this, because our update is not guaranteed to happen at a set interval, right? Sometimes update may be a little late. The amount of time that passed might be a little late. It's generally going to be your frame rate, but it's going to be dependent on how things are going, right? Different machines are going to run at different frame rates altogether, but also within any particular machine, your performance will change sporadically up and down. Sometimes your update has a little bit more time, a little less time. That's why we use time delta time, so at least to scale the step accordingly, so we know what that step is. That's what we're referring to as that delta time. But it's still potentially sporadic, potentially varying, right? So to answer that, to get around that, to kind of at least make the error something that is manageable and consistent, Unity provides this great function, this great event called fixed update. And the core thing about fixed update is that it's not just something that happens after update or before update or anything like that. It has it's part of a different loop inside of Unity. So Unity has basically multiple update functions which fall into two categories. There's two categories, the main loop category and the physics loop. Okay. The main loop runs at frame rate. The physics loop runs at something different. So they technically aren't running simultaneously. They are actually interleaved, and they're interleaved unevenly, but we'll see how this works, right? Update is running the main loop and is run once per frame, however often that may be. And fixed update runs in the physics loop, and it runs as regularly as possible, regardless of the frame rate. Okay, so the physics loop has some additional characteristics that allow it to interrupt what's going on the main loop, so that it will happen at a consistent rate. So looking at this diagram, you can see this graph, you can see, not graph, this, yeah, it's more diagram, chart, I don't know, this, yes. It's not yeah, anyway. So fixed update is happening at a regular interval, so 20 hertz perhaps, 50 hertz, something like that, versus update happening as often as it can, right? Subject to the stuff that's going in there. Now you want to be careful. You can cause problems here. You don't want to be just like running lots of code in here, or even potentially doing something nasty like having an infinite loop in here. We never want to have infinite loops in either of these, but we want to be careful about how we spend our time. We want to be careful to not kind of clog things up. And there's some ways to help mitigate that. This is one of these things called CoRoutines, which are a really handy thing that we can use. So going back to our diagram of what the Unity engine really looks like now we can see where is that physics loop. So we have the awake, the start, the normal loop, which is our user interactions, our interaction events, our update, and so on. Our animation step, that's what Unity is calculating for us based on how we've set up our animations, and then ultimately our render, and that's happening in one loop. And then our physics loop happens simultaneously with this fixed update that we can write, that we can supply, and then also any of our physics-based functions, our physics-based events, actually occur within that physics loop. So you didn't even realize it, but you've been using the physics loop this whole time, assuming that you've been using collisions, which I know you have. So if anyone has any questions at any point, feel free to jump in. Otherwise, I'm just sort of trying to be, I'm performing to an audience of, I don't know how many. Okay. Eventually I'll get tired of saying that. I'm still a little nervous. Okay. So your on collisions, your on triggers, they happen as part of that loop over and over and over again. All right. So one of the things you might ask yourself is, what is that interval? The other one is frame rate. What is this interval? How often do these occur? Now, you can set this. This is one of the things you can set. If you go to the engine, and during these lectures, if you can, depending on, hopefully you have a really nice big desktop monitor at home, maybe, or two monitors. And on one monitor, you can have the video playing, and the other one you'll have the Unity open. Go ahead and check. So if you go to Edit Project Settings, Time, you will see, and this is on the Mac, so if you want to see it on the PC, I'll take you over here. So here we are. So if I go to Edit Project Settings, so we're seeing the whole list right here, and Time, you'll see Fixed Time Step, which is frame rate independent interval that dictates when physics calculations and fixed update events are performed. So it's set at an interval of 0.02, so in other words, 50 times per second. That's how often this is happening. There are some other parameters here which you don't need to be too concerned about. So this is the worst case scenario for that when frame rate is slow. And you can also set the time scale. This is an interesting one. Some people have done this in their project. If you want to tweak this, the cool thing is this is affecting the time scale of the physics loop, right? So you can, inside your code even, slow down and speed up time in there. And the maximum time that should be allowed to process particles for a frame. We're going to talk about particle systems in a future lecture as well, so that's one of the other time things you can change. But for now, fixed time step is the important one. All right, so you get to set that. Most of the time, you just want to leave it what it is. 50 times a second is pretty darn good. All right, let's jump back. Where am I here? Sorry, you see my coronavirus chat. Let's see, presenter view. Here we go. That's what I wanted to do before, and I forgot. Back here. Where's my full screen? I lost my full screen. Oh, well, that's okay. Whoops. All right. Now, the bottom line, what does all that mean? When do you want to use this? When do you want to use fixed update? All right. Hold on, I'm going to take a sip of tea. And if anyone's wondering, I am drinking a vanilla rooibos tea. So, very good. Decaffeinated, thankfully. So the bottom line, from now on, when in your code, when do you want to use fixed update? Ideally, any code that manipulates a rigid body 2D should be contained within fixed update. Okay. This will assure you the smoothest or the most consistent performance of your physics, right? So if you want to accelerate an object, you want to change the velocity, this is chances are where you're going to want to put it. Put it in your fixed update. It's the safest place to put it, because this way your code, your physics will be consistent, right? Doesn't matter what machine you're on. Any modern machine is likely going to be running perfectly fine at 50 hertz running the physics loop, so you'll get reasonable performance, right? So when you are manipulating physics entities like rigid body 2D, you want them to generally be within the fixed update. Is that completely necessary? Is it a do or die kind of scenario? No. We've gotten around that so far, and then you probably noticed in the examples so far that I've shown you, I haven't really used fixed update for those, but it will have an impact on the smoothness of playback, as some people have noticed when they did the exact same code that I had on the screen. Mine performed a little smoother than theirs did, so on. Okay. If you are, that's not to say that any time you touch a rigid body, you have to do it inside of a fixed update call, right? If you're just setting an initial state of a rigid body, if you are doing a one-shot adding a force to a rigid body, things like that, you can generally get away with it just doing that in either of the loops. Okay. But if you want things to run smoothly, if you want things to run well, you may very well want to run things in fixed update instead of running them in update. Now, in certain cases, that means we'll often be separating out or decoupling input detection and physics movement. Okay, this is the safest way to do that. There are ways that you could do it that don't have nearly as much impact, depending on your model, depending on your character controller, and so on. But in general, the safest way to do it, and the most, a nice way to do it, is just to decouple them. So you have your input detection, like your on mouse clicked or clicked down, those sort of things that are user interface. You're going to separate those and then manipulate the physics in the physics loop. Okay. The way you're going to do that is by doing things like using kind of booleans as semaphores or as some kind of messaging in between. So, for example, instead of immediately applying a force or setting the velocity when you detect input during the update routine or in a on mouse routine, instead of directly doing something to the rigid body, you might set a flag, assign a bool, some bool that says apply forces or change happened, whatever you want to call it, and you set that, and then later on in fixed update, you check to see, okay, has that bool been set? Did that value change? And so on, and then apply the force and reset the flag or do whatever's necessary, right? So one simple case, if I run over to my code here, and I haven't made the change yet, but I will before next time, or maybe we'll do it outside of the class for everybody. The hero, for example, right now, the hero still does this the old way, right? The hero, and this is the version that would run inconsistently across multiple machines, right? The update routine gets the joystick, normalizes it, sets the speed, and so on, but then it directly adds a force here and potentially changes in here, checks for movement and so on. So that portion, let's see, the animation would be fine here because the animators happen in the same main loop, so it wouldn't be a problem. But this portion here, where I'm checking my rigid body's velocity against the joystick direction, this is the ideal candidate to move to the other loop. Okay. So I'll leave that. I'll condense this all down, and my examples, what I'll try to do is I'll try to condense the samples down into their own little snippets, their own clips that people can see on the other stream. Get a little bit of adjusting to Twitch to do here. Okay, so so what I would do is say, okay, joy direction here was a vector 2. Let's see if this works. We'll go for it. What the heck? Make it worthwhile. So I'm going to say, well, first off, joy direction here, I copied that. And I want to make this something in the class, so the whole class can refer to that, this joy direction. And here now joy direction is set every time in the update. It's going to detect that. And joy direction, it's going to normalize it, it's going to set the speed. And here was where I was setting it. And I will, for now, I'll just comment it out. Right? And I don't think I'm using last direction anymore. If you've watched the other tutorial, I've abandoned using last direction because now I use mouse aiming, and I'll talk about that. I'll leave that for there. So we'll do this. We'll say just that portion. If my rigid body dot velocity, so I'm going to check the velocity of the current of the rigid body against this joy direction, which is now something that everyone in all the functions in this class can see. If that changes, I'll be able to change it. So I'll say void fixed update. And so now it will look at the rigid body's velocity. If it sees it's not the same as joy direction, it will go ahead and set that. Right? So hopefully, see if I can come back here. We really shouldn't see any change. I'll just do the movement here. All right, so there's no change. But if I ran this on different machines, it would be far more consistent. Right, so his movement would just be correct because I've set that update interval now, that change in force, that application of those tiny little forces, they're happening at a consistent rate no matter what machine they're on. Okay, so once again, I have moved this, which was my manipulation of my physics object, my adding a force at some tiny interval. In this case, that interval, basically I'm changing the joystick, I'm reacting to the joystick as quickly as the screen is being updated and adding tiny, tiny little slices depending on, well, it depends how quickly the frame update is going on. That's going to be impacting how tiny those slices are. So by moving that out of that loop, I've made it consistent, right? So I know now that my time slices, that my intervals for adding force are consistent. I'm not just accommodating it using time delta time. Time delta time is a way to kind of smooth things out, to make sure things don't get completely out of whack, but this is really a way to make it consistent, right? Even with time delta time, there's a limitation on how that is, especially when you're talking about, potentially with physics. So this really makes that work right. All right, let's jump back to the thing here. All right. Okay. So I just did it. I decoupled input detection and the physics movement, right? Now, let's talk about another thing that this potentially, and this is really not the sort of thing I'd want to do, not the sort of thing I'd really recommend. I'm going to introduce a concept in here that we'll talk about. I think we're going to talk about it later in the week, interpolation. So I'm going to kind of gloss over it a little quickly here. So imagine I wanted to have something that sped up and slowed down, right? I want, instead of having some sort of linear motion or even an exponential increase in motion, I wanted basically sort of what they call a logistic function, right? Logistic function. Just had an argument with someone over this. It's basically things speed up slowly, and then they reach a certain velocity, and then they tend to, well, they speed up slowly, speed up at a certain rate, they reach that speed, and then they tend to kind of slow down or come to rest. Also, they have a deceleration, right? So it's not just a straight linear curve. They slowly start up, and then they slowly decelerate, sort of. So interpolation, what interpolation does is allows us to, you can just do a straight linear interpolation. You've probably heard about that, where you just say, okay, over the course of time, if I want to know where I am at any particular moment, I use time as the way of saying, okay, what portion of time has passed, and give me the value according to that, right? 50% of the time having passed, I should be 50% of the way there. 75% of the time passed, I should be 75% of the time there. 75% of the way there, that sort of thing, in a straight linear interpolation. And there's going to be other forms of interpolation we're going to use that are more like these logistic functions and exponential functions. So I'm getting sidetracked, sorry. Okay, so in the case of interpolation, and lerp, here we are, lerping. It's not like LARPing, it's lerping. So we're interpolating, and we're going to say what we want to do is we want to assume a certain time, and there's going to be a value that we start at and an end value that we want to get to. And we want to interpolate from the start value to the end value over the course of time. So we say the total amount of time I have, and we say that the starting time is the time we're currently at. We look at the clock on the wall, that's what time it is. And we say, all right, the time that has passed is the current wall clock time minus the time we started at. I look at the wall clock now, I say, it's 11 o'clock. I know I started the class at 10 o'clock. Therefore, an hour has passed. Wow. I'm talking for an hour. So if I wanted to interpolate the class, I know I have 2 hours to go total. I'm not going to talk the whole time. We're going to stop earlier than that. But this is what the lerp time is. How much time is in the interval? How much time is the class, right? So I started, I know how much time has passed, and ultimately what I'm trying to figure out is what portion of the class has passed. I'm at 50% right now. So if I said current time, I have 1 hour has passed, and my total time is 2 hours, so I'm halfway into the class. So I can say, okay, how much material have I covered? I say I started at 0 material covered, and I want to get to 100% covered. And if you said, okay, at any particular moment in time, tell me how much material you've covered. So what I'm doing here, what this illustrates, is to say it's really calculating a new position to move an object to. So a new position of an object is going to be calculated based on the starting value, the ending value, and the amount of time that's passed, and it will just interpolate. It will blend this value and that value according to this ratio. We're going to get more into that the next lecture as well a little bit. So that's what's going on. And that's our loop. We said, okay, while this is happening, we want this to happen, right? So we know at some point, we look at the wall clock time, we subtract the current time, that gives us the amount of time has passed, our delta time, and we calculate that over and over and over again. So can anyone tell me what's wrong with this picture? If I wanted to really use this and I put this in my update, or even put this in my fixed update, what would happen? Somebody type in an answer. Would the object move? Drinking tea. You guys got to get more brave about typing. I know, you're the brave ones. Come on. It's the battle of wills here. I got to break down and explain it. Well, in the interest of time, anyone typing? No. All right, in the interest of time, pardon the pun, the problem is with a while loop like this, even though time.time may be passing, we're never updating anything on the screen. We're never saying, okay, now give everything else a chance to work. Give the animations a chance to happen. Give the motion a chance to happen. Actually render the frame. None of that's happening, right? There's no sense of time slice here. We can never get out of this loop until all the time has passed in that loop. So even if time.time does the right thing and this loop runs for 2 seconds, nothing got a chance to be updated, right? So this is not an infinite loop as long as time.time continues to pass. But it also is not a useful loop because it's not going to do anything. It's going to kind of sit in there for 2 seconds and do all these calculations that never impact anything on the screen. Best case scenario, it doesn't update the screen. Worst case, it clogs the machine for 2 seconds. So how do we get around that? Big concept. CoRoutines. CoRoutines are your friend. CoRoutines are like one of the most useful things and one of the important things to kind of understand inside of Unity. Okay. CoRoutines are the big cousin, the superhero version of sort of the invoke functions that you've seen. We had invoke and invoke repeating. So there was sort of a special case, and we don't ultimately. They're quick and dirty functions using invoke and invoke repeating, and they're kind of limited in their usefulness and how you can tune them, right? So what's more powerful, what's more useful, what we recommend you use most of the time are coroutines, because you have a lot more control over them, and you have a lot more control about when they're spawned, how they run, and so on and so forth. So they are special functions that are executed according to intervals, right? They are functions that also can exit prematurely. So before they're done, basically, before they have entirely executed, they can say, okay, I need to exit for a bit and give the system chances to do other stuff, right? This is basically an early return, right? Sometimes functions could say, oh, okay, return before they've executed entirely. You can embed a return anywhere in your function. It's kind of like having also like an extra, like a break inside your loop. You can exit early from a function, but the cool thing about coroutines is they resume after some amount of time, and they resume exactly where you left them, right? So that's all automatic. You don't have to worry about that. You don't have to do the recursive bit and the clever tricks that we played with invoke repeating, right? This you can just say, all right, run, pause, yield based on some action or some condition, and it can happen again. So it's like you're able to create sort of your own little loops, so your own little whiles that are not going to clog the machine, hopefully. Okay, so they're super useful for kicking off little processes that need to run over the course of several frames or over the course of some amount of time, but they also can just run on their own. So the logic that's in them can be much more straightforward and simple, right? They're great for routines that have to wait for another operation to complete. So if you said, for example, oh, the missile can't be launched until the user has done this, that, and the other thing, right? You can have it kind of sit there based on some condition. It's going to, sit in a loop just waiting to happen without having a million different things in your update routine. Check this, check that, check this, right? You can set up these functions and then they happen on their own without clogging up your update routine, for example. So let's take that same function and we'll do it as a coroutine, all right? So we said, okay, here's our function, IEnumerator, and that's the big change. You have an IEnumerator instead of just saying public void. IEnumerator says, yes, this is a coroutine. Now imagine we jump in, we have a starting value that's negative 5.42. We have t, which is going to be our time. We have an ending value that we want to get to. We know we start at a certain time. We want to interpolate. So this is all the same. That stuff is all the same. And even the while loop looks very, very, very similar, right? The condition's the same. We're waiting for those 2 seconds. We're waiting for the 2 hours in the class. You guys are eagerly waiting for me to stop rambling. You're calculating faithfully each step along the way, and you are then moving according to that. But we have this yield in here, yield return null, and that basically says, okay, yield until the next update, right? So it jumps us out of this code and says, okay, we're done for now. We run one iteration, run one run through the loop. Okay, so it will be limited. There are limitations according to the frame rate. You can't necessarily run coroutines at crazy intervals because they do happen at specific points within the code. That's why we talk about coroutines in the context of sort of the way the engine runs, right? Now, the other thing before I got into the other part is, well, how do you call a coroutine? Similar to invoke repeating or invoke, except it's got its own version. It's called start coroutine. And there is a very important difference. You'll notice that here it is just invoked or started, and you don't have to put it in quotes. So it's different than invoking. Starting a coroutine is different in that you say move parentheses. So it looks like you called the function. Okay, looks like you actually called the function and passed that to start coroutine. right? You're passing it really the function. You're not passing it the name like you would with an invoke. Okay, that's important to remember. So that yield, let's talk about a couple of things. You don't only have yield return null, which means happen, every frame or every fixed update depending on how you're doing things. But normally that's the first one you try, right? That happens at a certain thing. You can also say yield break, and if you yield break, it just immediately stops the coroutine, quits execution, gives you a way to cleanly run that coroutine and then just have the coroutine stop on its own, right? Stop the coroutine at that point in the code. One thing that's very cool, very useful, is this notion of saying yield return new wait for seconds. So if you have a function like, say, dropping apples or changing speed or whatever, you can have your coroutine decide to say, okay, coroutine would look like just saying, okay, change the speed, wait for seconds, and then wait for seconds would be some random number of seconds, and then it just runs in its loop again next time around. So you can have a while loop that all that while loop does is every iteration through the while loop, it changes direction. And what you're modifying is every time you call yield return new wait for seconds, you give it some random time interval. So that'll give you your random drops of apples or your random changes of direction nice and cleanly without having to worry about other things. So that's kind of cool. Another one, yield return new wait for end of frame. So you can have your coroutine specifically wait until reaching a certain point in the code, right? You can wait for fixed update to happen. So it executes at the next physics step after all physics are calculated. Or you can even yield until another coroutine finishes. And this is a little bit more elaborate. I don't think I've seen anybody really use this in any of their projects just yet, but it's out there as well. So let's look, and this is the whole thing. This is the entire Unity, or at least as of the older version now, if you're not using the Unity ECS and so on. But anyway, the normal Unity loop looks like this. So during a frame, we have the things we've discussed on mouse, update. Then we have our coroutines. Those are the ones that when we say yield null or wait for seconds, those are being called in the frame loop, right? So there is a maximum. You can't wait for an interval that is smaller than the frame rate of the machine you're running on. You can ask for it, but it won't happen, right? That's how fast it can happen. After that coroutine, those coroutines happen there, or where that wait is, then animation, late update, and rendering can happen. If you say, yes, yield wait for end of frame, it will resume there. So, kind of cool thing, you can say, run this code, yield wait for end of frame, this, and this will happen, and then your code will get called again. Okay? So you can cause your code to run twice in the main loop. So that might be one way to, if you really wanted to have something happen faster than, sort of faster, or at least twice per loop, you could do that. Other ways to do that as well. So anyway, don't get too clever. And then within the physics loop, you can also have coroutines executing according to wait for fixed update, right? So if you want to have something that is happening based on the physics update interval, you would say wait for fixed update, right? So if you wanted something to happen every 50 hertz in our case here, we would say wait for fixed update. Okay, that's the end of the lecture notes. Let me show you a practical example of that. And I use this at the beginning here. We had our little game. I won't shoot too many things around. But here's our little character. And you'll notice our character is doing this weird kind of glowy thing. And the glowy thing is nice and smooth, and it doesn't matter how I'm moving around. And it also glows, and it doesn't get too clogged by the fact that all of those pinging coins were happening. Everything's nice and smooth there. So how is that happening? Let's look at the example. We'll go to the code for our hero. And at the beginning of hero in start, so I started this coroutine at the start of the hero's function because I don't need to do it in awake because it's not visible until you start, so that makes a perfect sense. Just put it in there. And I said start coroutine myGlow. So I start this function, I kick it off right after the start happens. And I've created this simple function called myGlow that is declared as an I enumerator instead of a public void or a private void. It's just an I enumerator, myGlow. And within myGlow, there is some just simple code, and it's an infinite loop in here. First thing you'll hopefully immediately notice this scary looking while true, which normally we would definitely not want to have in an update function or a fixed update function. While true, scary thing. But in this case, it's not scary. All right. So we do, going into while myGlow, we start off, we have a temporary or just a local variable called temp, which is initialized to 0. And then we say while true, we increment temp by 0.01. So we increment it by 100th. And we also modulo, we take the remainder when dividing by 1. So that means that temp will go between 0 and 1 over and over and over and over and over again, potentially, in this while loop. Every iteration through, it's going to go up by 100th and enforce it to be between 0 and 1. And then I'm going to use that. I'm going to use that to specify a color for the sprite's renderer, right? Even though the sprite has an image, we can assign a color to it, right? We're not going to do anything too elaborate. I'm just basically, there are ways to say, okay, what does the sprite do with regards to that color? You know, how does the image interact with that? But for this part, basically what I'm doing is I'm changing the brightness and the opacity or the alpha value, right? So this is, since I'm using the same value for R, G, and B, it's just going to be a gray that goes from 0 to 1. So I'm going to be setting that color as a gray level from 0 to 1, and at the same time modifying its opacity from 0 to 1. Excuse me. So that's what's going to happen. I want it to glow. I want it to kind of go up and down like that. It's a sawtooth. It goes 0 all the way up to 1, drops back to 0 again here. It's not a triangle wave or a sine or something. I could do anything. You could calculate like that. Use the sine function there. Well, that'd be interesting. But for now, I'm just doing this kind of sawtooth function, right? It ramps up, drops down, ramps up, drops down. And then every iteration through the loop, you'll notice I said here, yield return new wait for seconds. And I say, okay, wait for 1,000th of a second. So if I only waited for 1,000th of a second and I ran as quick as possible, boy, it should actually update pretty quickly. But you'll notice that this is still happening far less than 1,000th of a second, or it's not happening that quickly. Reason being that this wait for seconds is subject to, as I said, in here, wait for seconds happens in your update loop. So effectively, you can't run that fast. On my machine, my computer here, I'm running at about 144 hertz or up to 144 hertz. So that's the limiting factor on how quickly this code is really running. If I do something that's way lower than that, like said, okay, run at 1/10 of a second, that would definitely have an impact. So let's go over here, play. Okay, that's having an impact. We're running much slower. We're running basically now at 1/10 of a second, right? 10 times per second we increment. So it's going to take 10 seconds to go from 0 to 1, right? So I've slowed things down. It's going to calculate. So I don't have to deal with this. I don't have to think in terms of frames per second or anything like that. Unity is handling that part for me, which is nice of it. So at least I'm dealing with it, wait for seconds. I don't have to say, well, wait for 7 frames, because that would be ugly. So, excuse me. So there you go. That's a simple use of myGlow. Now, It could very well be something like you might use my glow or kick it off to say, okay, glow, blink 3 times and then exit. Right, so I could have another counter in here that would say, oh, okay, once this runs 3 times, then yield break, yield return break. Yield break, and now I'm forgetting. I don't use that one often enough. Yes, yield break. To stop the coroutine if I wanted to. So I could have it, oh, okay, every time the user gets hit by an object, I could create my own little animation here. So you get hit by the object, you start a coroutine that causes you to glow or fade. Once you're done fading, stop the coroutine. That sort of thing. All right. So that's it for today. I'm going to wrap it up there. Thankfully, a little bit quicker than yesterday's. So this will become the preferred one. If you want to refer back to a shorter version, this is the one. And if you have any questions about things, go ahead, contact me through Discord. I'm going to use class time as the definite times I'm going to be around. Usually I'm at my desk all the time, so I'm not going to have specific office hours because just contact me on Discord. I have my phone with me just about all the time. Get your if you have something specific about your game that you're working on, make sure update it, upload it to the Unity cloud, save your changes, push your collaborations, and so this way I can open it up. And often what I'm going to try to do, I may do some check-ins, I may actually put some comments in your code and kind of do things on that basis, especially if you've got kind of office hours-y kind of questions. And if you're not in the same time zone, I know some folks are in other time zones, we'll deal with that. Okay, and last but not least, I will ask, I'm going to put no questions. And if you have no questions, go ahead and react. Give me a thumbs up on that one so I know that I can kind of shut down the stream, and we'll leave for today. This will be live at least for 2 weeks on Twitch for you to refer back to. And if it feels to me like it's good enough to keep as part of my developer blog, developer vlog, whatever, over on my YouTube channel, I'll push it up there. So we'll do that. If you have any questions about anything else in general, I can't say like I'm certainly not on campus every day or anything like that. I'm not even sure how our interdepartmental meetings are going, and so on. So if you do have any general RPI questions, please run it through the normal means, but also feel free to reach out to me and I'll try to shake the trees. If you haven't already joined the GSAS server, the GSAS Discord server, or the RPI Discord servers in general, go ahead and do that. Great way to keep in touch with people. And by all means, do interact as much as you can with folks on Discord, Facebook, social media. Who would ever thought it would come in so handy? And if you are interested in kind of exploring it, basically turning your project potentially into sort of a more data intensive or even sort of communications intensive educational tool, informative tool to kind of show people, hey, this is how things work. With regards to anything, we can certainly do that. These simulations are an opportunity for us to be able to sort of use what we're good at as game developers, as communicators, to kind of reach a broader audience that who might see like a real scientific visualization, be like, oh my God, I have no idea what that means. But they will understand what happens when you bounce coins and they keep repeating and so on. All right. On that note, everybody, take care. Have a great day. Stay safe. Be well. Don't drive everyone else in your household crazy if you're lucky enough to have people around you. If you're not, hey, feel free to reach out. We're all here for you too. Take care now. Shutting down the stream. Thanks for joining us via Discord or Twitch.